So the probability of just getting x equals 3. So the probability of getting a red counter. So red is 3 out of 10. Okay. So the probability that we get 3 red counters is, well, the coefficient is going to be 5, 3. Right. The probability that we get 3 reds is 3 over 10 to the power of 3, and therefore the probability, the other end of it, is 7 out of 10 to the power of 2. So then we've just got to evaluate that. So 5, 3 is 10. So we've got 10 times 3 over 2 cubed times 7 over 10 squared. You work that out, whatever you get. Back to recording, so you're aware. The probability then, the probability that x is greater than 1, well, actually, as you pointed out, is the probability, actually, sorry, should have done, it's 1 minus the probability of x equaling 0 plus the probability that x equals 1. Okay? Makes sense? So this one would be all blues. So it would be 5, 0, which is 1. Yeah?
Yeah.
1 times the probability of getting a red is still 3 over 10, but I want 0 of them, times 7 over 10 to the power of 5. So that's 1 times 1 times
0.168 or something.
Okay. And then the probability that x is 1 is 5, 1 times 3 over 10 to the power of 1 times 7 over 10 to the power of 4.
So that's 1 times 3 to 10 times what? Distribution.
Is that a 1?
It's not, it's 5.
I'm going to say it's a 5. There are,
So
if I've got 5 things in front of me, there are 5 different ways that I can select one of them. Okay. So when you work that out, we should now have the correct answer to subtract from 1 to find out the probability that x is going to be greater than 1.
Why is it to the power of 0?
Because I get none of them. Yeah. So if you think back to tree diagrams, the tree diagram would be red, blue, and so on, yeah?
Yeah.
So if I'm choosing the probability that x is 0, that is a blue, blue, blue. And how do you find that out? It would be, well, that's 7 over 10 times 7 over 10 times 7. How many 3 over 10s am I multiplying in that line? None. I would just have 5 7 over 10s. Yeah. Whereas, how many options are there to have 1 red? Well, it would be 1 red, and then it has to be all the blues. But then it could be a blue followed by a red, then blues. It could be a blue, blue followed by a red, followed by blue. So there are obviously lots more options. When in fact there are 5 options for doing that. Have we got a final answer this time? Correct one?
0.59, but that's with the way of just doing 7 over 10 to the power of 5 minus 7 over 10 to the power of 4.
Don't agree, okay? You got what? So is that what, did you give us this number?
0. What?
The number in the parentheses is 0.5, then I don't know.
0.5 something, therefore we've got 0.47.
It should be 0.5282, yeah.
So 0.53 and therefore 0.47
Oh,
is the
yeah,
probability.
I did get it.
Yeah.
Yeah, because I just had to put in 1 for the binomial.
With hypothesis testing, just an exam kind of formal tip for you. With hypothesis testing, one of the main problems with it is the formal structure to your answer. Okay? You have to meet certain criteria for a correct full answer. So it's not the case where you just write a number at the end and have done. There is now going to be some writing involved. Okay? And we should talk about what hypothesis testing is. Okay? Which I won't put on the video because that'll make it boring, but you can always read it, but I'll say it. So, a sociologist believes that more boys than girls are born during wartime. In a sample of 200 babies born in countries at war, 116 were boys. So they're making that statement because there was a lot of boys and not many girls. Okay. What we're going to do though is look at how likely that amount of boys out of 200 was. All right? And whether we think that number is statistically significant or not. Does that make sense? So we're not just going to look at the number. Now, here's the thing, obviously you know about stats, is depending on what levels you, what numbers you tweak, you can make things say one thing or another. That's what people do. But here's the formality. So let's go through. You understand the situation we're talking about, yeah? Yeah? Okay. So we're going to write these things down. So we're going to say, this is the formality to the answer. So it's not to me, this is what you will write down. Let P be the proportion of boys in the population. Okay? So what I've done there, which is important, is define the variable. So now I can use this P. Right? I can write P equals P is greater, that kind of thing. So you have to define what your P is. And if you don't, you can lose marks. Okay. This is where you might come up against something new, which is H with a little 0. Anyone know what that is?
No.
No? Tell you in a sec. But we say P is equal to 0.5. This is stating, so you've got to state what you call your null.
Said that.
Sorry, I didn't hear it.
Okay.
Null hypothesis. So what does that word null mean? You might have had it in quadratic factorization, like the null factor law. It's when you factorize, because when you make one of those factors 0, it nullifies everything, right? So basically, the null factor law is the default standing, which means the whole thing is like just equal. So why have I got P as 0.5? Well, my null default standing is that if the probability or proportion of boys in the population is 0.5, we're saying it's 50-50. 50% girls, 50% boys. So that's our default standing. What we then have is H1, where we say P is greater than 0.5. Because the statement in this question was, in wartime, there are more boys than girls. So if P is the proportion of boys, we're saying this hypothesis is that P is greater than 0.5. This is called your alternate hypothesis. So you need to state your alternate hypothesis. Or alternative, I guess. All right. We've not got much time left. So I'll finish on one final thing that we can start then next Wednesday. Oh, yes.
Double mark.
You have. No, next Wednesday.
Yeah, but we actually have the tests on
What are
Wednesday.
we doing then?
Oh no, but
So the